Welcome to The Explainer. Today, we're diving into a massive paradigm shift happening in one of humanity's oldest, heaviest industries, mining. But forget the giant excavators and underground explosives. Instead, we're going to look at how microscopic life is stepping up to solve a massive global mining challenge. It is literally a story of how the very small is completely transforming the very large. Okay, let's dive right into this because I want to start with a statistic that absolutely blew my mind when I first saw the data. 20%. Just hold on to that number for a second. When you think of where our raw materials come from, you probably picture massive industrial operations, right? But nature has its own invisible workforce operating at a scale that is genuinely hard to comprehend. Did you know that microscopic bacteria, literally bugs in the dirt, are responsible for over 20% of the world's primary copper production? It's true. 1/5 of all the new copper entering our global supply chain isn't just dug out and smelted in the traditional sense. It is literally being extracted by specialized microbes with a heavy metal diet. It's an incredible hidden impact, and understanding how it works is absolutely crucial for the future of our resources. So that brings us to Section 1, the Global Mining Challenge. To really grasp why these microbes are such a game changer right now, we need to talk about bioleaching. Basically, our high-grade ore deposits are rapidly depleting globally, and we're left with this really complex, difficult rock. Bioleaching solves this. The technical definition is a process driven by microorganisms to oxidatively solubilize sulfide minerals. But honestly, in plain English, it just means we're using specialized bacteria to break down low-grade rock, dissolving the valuable metals trapped inside so we can easily collect them in a liquid. We are deploying biotechnology directly into the dirt. Which leads us perfectly into Section 2, Meet the Rock Eaters. Now, what's really interesting about this is that these rock eaters aren't your everyday household bacteria. They're extremophiles that feed off inorganic energy sources. We actually categorize these biological miners by the extreme temperatures they prefer. First, you've got your mesophiles thriving right around 30 to 40 degrees Celsius. This includes the highly researched Acidithiobacillus ferrooxidans. Then we step it up a notch to moderate thermophiles at 40 to 55 degrees. But the absolute heavy hitters, the extreme thermophiles, these resilient organisms thrive in highly acidic environments at up to 90 degrees Celsius. I mean, that is literally near boiling. But, it's not all smooth sailing. The primary biological hurdle scientists run into here is known as the passivation roadblock. Basically, as the bacteria chew through a mineral like chalcopyrite to get at the copper, a chemical reaction happens. And this reaction creates a tough crust of sulfur and a mineral called jarosite that builds up right on the surface of the rock. Think of it like a microscopic suit of armor. This crust essentially blocks the bacteria from reaching the unreacted rock underneath, which totally slams the brakes on the copper extraction. So how do we bust through that armor? Well, the source research highlights some brilliant scientific innovations. Engineers are running these systems under strictly regulated redox potentials, and they're introducing additives like silver ion chloride ion systems to speed things up. But one particularly fascinating approach uses wash solutions made of sodium and ammonium carbonate to essentially wash away that stubborn passivation film. And the results speak for themselves. The data shows this specific washing technique can actually achieve an 11% higher copper recovery compared to traditional bioleaching. All right, moving on to Section 3, copper bioleaching at scale. Now, when we zoom out, how does this actually work in the real world? You might be picturing giant indoor science labs, but for copper, the real magic happens outside using massive heap leaching. It's a wild process. Step 1, they crush millions of tons of low-grade minerals into little pieces, about a centimeter or so in size. Step 2, they cure it with diluted sulfuric acid. Step 3, they stack it all up into these gigantic heaps. But listen, these aren't just piles of rock. They are highly engineered bioreactors. They have pipes running all through the bottom, pumping in air to give the bacteria the crucial oxygen and carbon dioxide they need to survive and grow. And finally, step 4, an acid solution trickles down from the very top, percolating all the way through the heap, dissolving the copper as it interacts with the microbes until it pools at the bottom for collection. And this brilliantly illustrates just how massive this already is. Global copper giants are leaning heavily on this biological technology. Bioleaching currently drives a staggering 42% of total leached copper production down in Chile and 33% in Peru. So we're not talking about some experimental sci-fi future tech here. This is the current, everyday backbone of modern mining in these regions. Let's shift gears a bit. Section 4. Unlocking refractory gold. So, moving from copper to something a little more precious, gold. The huge headache for miners here is something called refractory gold ores. In these specific deposits, the gold is incredibly fine and it's physically locked inside a microscopic cage made of sulfide minerals. It is so tightly bound up that conventional cyanide leaching, which is the industry standard, is completely, totally ineffective. The chemicals just bounce right off the cage. They can't even reach the gold. Historically, the only way to crack that sulfide cage was pure brute force, smelting or roasting the rock at insanely high temperatures. But that old-school conventional mining brings high toxicity risks and absolutely massive capital costs. Enter bio-oxidation. By deploying our extremophile bacteria to literally eat the sulfide cage, we get an incredibly environmentally friendly process that leaves behind safe, stable residues. And here's the real kicker. Studies show that building and running a bio-oxidation plant actually costs 50% less than conventional smelting and refining. 50%! That is a massive reduction in capital cost.
So, what's the actual sequence here? How do the bacteria act as the unlocking mechanism? It's a precise three-step pretreatment process. Step 1. The bacteria go to work oxidizing and tearing down those sulfide minerals to liberate the hidden gold particles. Step 2. The leftover acidic residues get treated with an alkali to neutralize things. Step 3. Now that the gold is finally exposed and unprotected, standard cyanation can swoop in and actually do its job. To put that into perspective, without this bacterial pretreatment, gold recovery from these complex ores can sit at a miserable 6 to 40%. But add bio-oxidation to the mix, boom, recovery rates rocket up to over 95%.
Now, to get those kinds of optimal numbers, gold extraction is usually done in huge, carefully controlled, agitated tanks, rather than those massive outdoor heaps we saw with copper. And commercial bioleaching plants are thriving all over the globe right now. You've got BIOX technology using massive stirred tanks sitting at a 20% concentration with a 4-day microbial residence time. You have the BACTEC system out of Australia operating at 50 degrees Celsius specifically to utilize those moderate thermophiles we talked about earlier. And to really grasp the massive scale we're talking about here, the world's largest bioleaching plant in Uzbekistan processes an astonishing 2,163 tons of gold-bearing ore every single day. So the crucial point is that the industry isn't just sitting still. They are constantly iterating on these biological systems. The source highlights technologies like the Albion process, which offers a highly efficient biological alternative to traditional high-pressure oxidation. And as the research notes, it delivers a shorter project implementation time, reduced technical complexity, and incredibly reliable metallurgical performance. Basically, we are taking one of the most complex, difficult industrial processes on Earth and simplifying it immensely just by partnering with nature. And that brings us to our final act, Section 5, the ultimate cleanup crew. This is where the whole explainer takes a fantastic plot twist. Because these microbes, they don't just mine, they moonlight as the world's most powerful environmental janitors. Through bioremediation, these biological systems have literal superpowers when it comes to pollution control. They're actively deployed to destroy toxic cyanide left over from processing, both inside the treatment plants and out in the waste piles. They actively prevent acid mine drainage, which is arguably the single most severe environmental threat in the mining world. By using active and passive biological treatments, these tiny organisms literally break down highly toxic compounds and transform them into nothing more than harmless water and carbon dioxide. It really shifts your entire perspective, doesn't it? We have spent centuries trying to conquer the Earth with explosives, heavy machinery, and fire, only to realize the most efficient, cost-effective, and environmentally safe miners and cleaners were already right there in the dirt, just waiting for us to utilize them. Which leaves us with this final thought. If microscopic organisms can revolutionize our oldest, heaviest industry, extract our most precious metals, and clean up our most dangerous toxins, what other massive global challenges are just waiting for a microscopic solution? Thank you so much for joining me for this explainer, and keep questioning what's possible.